circuit is designed to add 3 binary bits, which is input A, input B, and carry in C in. The circuit is formed by 2 half-adder connected in series. To calculate the sum, which is S, I use 2 XOR gates. The first XOR combined with B inputs, and the second XOR gates add the carry to that result. To calculate the carry out, which is C out, I use 2 AND gate to detect when 2 or more inputs are 1. These are then connected to an OR gate to produce the final carry signal. When input A equal to 0, B equal to 1, C in equal to 1, and then we will get the outcome sums remains 0 while carry out C out becomes 1. This correctly represents the binary operation, which is 0 plus 1 plus 1 equal to 1, 0. When inputs A equal to 0, B equal to 0, and C in equal to 1, the sum, which is S, rise to 1, and the carry out C out drop to 0. This successfully demonstrates the binary operation, which is 0 plus 0 plus 1 equal to 0, 1.
4-bit adder or subtractor is made up of 4 1-bit full adder, and to differentiate its function as an adder or a subtractor, the carry in N and each input D are connected to XOR gate. So when N is set to 0, this circuit will function as an adder, and N equals to 1, this circuit will function as subtractor. So we connect the input A to the each 1-bit full adder, and the result from XOR gate will connect it to the full adder too. So it will produce the sum here, output sum. Now let's run it.
So from the result, when M equals to 1, the circuit function as a subtractor. So A equals to 0011 and B equals to 0000. 0011 minus 0000 will become 0011. So at this part, when M equals to 0, the circuit function as an adder. So 0001 at 1010 will become 1011. The simulation result is all correct. 4-bit XOR gate, we connect it is made up of 4 1-bit XOR gate. Then we connect our input A and B to the XOR gates. Then it will produce the output, 4-bit output here. So now let's run. Now let's look to our simulation result for XOR gates. So for this part, when A equals to 1000 and B equals to 1010, the output will become 0010 as the XOR gate will function when same input the output is 0, different input the output is 1. So 11 becomes 0, 00 becomes 0, 01 becomes 1, and 00 becomes 0.
This is our design XNOR 4-bit circuit. So we have 2 inputs A, B, and each of the input will be separated into 4 bits. For bit 0, it will be connected into the first XNOR gate, bit 1 will be connected into the second XNOR gate, bit 2 will be connected into the third XNOR gate, and the last bit, bit 3, will be connected into the fourth XNOR gate. And the output, each of the XNOR gate will produce an output, and the output will be connected into the final XNOR output. So now I'm going to do the compilation. Compilation is done, functionality is verified. This is the waveform result that we simulated. So I will take 240 nanoseconds as an example. A is 1111, B is 0000. So the XNOR output is 0000 according to the truth table. This is our design 1 bit for 1 multiplexer. We have 2 main control signal, which is S1 and S0. We have 4 input, which are I0, I1, I2, and I3. So for S1, we connected it to I2 and I3, and for S1 bar, we connected it to I0 and I1. For S0 signal, we connected it to I1 and I3, and for S0 bar, we connected it to I0 and I2. So each of the inputs will be connected into an AND gate. For the outputs, they are connected into an OR gate, and we can have the final output here. We finished the compilation, and here shows there is no error. So this proven that our design is verified. So this is the waveform result that we simulated. So we take 160 nanoseconds as an example first. So we can see here I0, I1, I2, I3 are 0, 1, 1, 0 respectively, and S0 and S1 are 1. So from this we know that this is indicating into I3, which is 0. So the output is 0. This is the 4-bit 4 times 1 multiplexer. So each of the input here will create 4 bit. For bit 0, it will be connected into the first multiplexer. Bit 1 will be connected into the second multiplexer, and bit 2 will be connected into the third multiplexer. Bit 3 will be connected into the fourth multiplexer. Then each multiplexer also connect with the S1 and S0. Then each of the multiplexers will produce output, which is O. The compilation is successful, and this shows that the functionality is verified. This is the waveform result that we simulated. So let's look at example at 240 nanoseconds. So I0, I1, I2, I3 are 1111, 1111, 0000, 0000 respectively. So look at the selector S1 and S0. They are 0, 1. So this indicated into I1. So the result output would be 1111, same as the I1.
I have designed using D flip-flop in the quarters. We have 3 main control signal. First is D, next is the clock signal and reset pin. In the center, all D flip-flop. Each one acts as a 1-bit memory cell. On the right, individual outputs, all 0, true, or 3, are bundled back together into a single 4-bit output bus called Q 3.0. This allows us to read the entire 4-bit word that is currently held in the register's memory. There is a rising edge on the clock, while reset is low. When the input D is 1111, so the output Q will follow the D input and also get 1111. There's a rising edge on the clock, while reset is high. Even though the input is 1111, but Q is from 1111 back to 0000.
A loop is conducted with 3 blocks of 4-bit 4 to 1 multiplexer, 2 blocks of 4-bit adder or subtractor, 1 block of 4-bit XOR, 1 block of 4-bit XNOR, and 1 block of 4-bit register. So at first we connect 4 inputs and 2 selectors to these 2 marks, and then from the result from the marks we connect it to this 4 functional circuit. And for the first circuit, this adder is connected to GND, which the input is 0, so it will function as an adder. For the second adder, M is connected to the input, VCC, which the input is 1, so it will function as a subtractor. After that, the output result from the 4 operational circuits will connected to the marks, and the selector also will connect to the marks. So The output which is selected will connect to the register, and with the reset and clock also will connected to the register. To boost the final output, now let's run. For this part, the reset is set to 1, so the output result is clear to 0000. And for this part, A3 and D3 are selected to add up. So 1110 plus with 0010 will become 0000, a 4-bit value. For this part, A0 and B1 are selected to subtract. So 1110 minus 1001 equals to 0101. And this part, A1 and B3 are selected for XOR operation. So, and 1100 and 1101 will produce the result 0001. And for this part, A2 and B3 are selected for XNOR function. And 0110 and 1000 will produce the result 0001.